Now we'll consider the types of thermodynamic systems. We have three types. We have isolated system, we have closed system, and the open systems. And the difference actually lies on the interactions, if they can go, or I mean if they can go in or they can go out from the system. When I say isolated, that means it is isolated, so which means there is no heat nor mass can actually go into the system or go inside the system. So there's no interactions going on. And then when I say closed systems, that means uh, there's no mass that can cross the boundary, but we can have interactions for heat and also work. An example of this is a refrigerator. Let's say here's our refrigerator, and here's the front door, and here's the um, front door at the bottom, and this one is for the freezer. So at the back here we have condenser, and we we can actually feel the heat that's radiating. But since we have an we have a closed system here, that means that if we consider this as our thermodynamic system, then we can see that there's no mass that's going in or out to our system, but we can have interactions for let's say for heat, and we can also have, of course we need electrical work as well, so that's why we have heat and work, but there's no mass. Of course we are assuming closed doors, so that's an example. And then for an open system, since it's open, then that means that mass can actually go in and out of the system. So example of this is a pump. Let's say here's pumps or blowers, for example. Right, so let's say here's our pump. So pump is used um, for moving the water from one point to the other. So here's, let's say, an intake pipe, and let's say here's the discharge pipe. So we see that mass of water can actually go into our system and also discharge from our system. So if we consider that our thermodynamic system is the pump only, so that's one example. And then another one is for let's say fans, actual fans. So we see here we have um, air that is going into the system and air that is leaving the system. So that's an example of open systems. Of course, for fans to operate, it needs work as well, electrical work. Okay, and then next is, let's discuss or introduce the thermodynamic properties. So actually, when energy and or mass crosses the boundaries, there's actually a change in the system. Let's say here, initially we have a gas, and let's say we have this, let's say a cover here that can move up and down. So initially at this position, then if we take a measurement of its pressure, or let's say volume, pressure, volume, or temperature, then we can have a reading. Okay, and then if we because we introduce work into the system, and we consider the gas as our system in this example. So if we introduce work, let's say we apply force so that this one compresses, and if we take the reading, actually we can see a change in the pressure as well, and also in the volume and other properties actually. So that means at any point there is this characteristic of this system, and that characteristic is what we call the thermodynamic properties. So there's actually a lot of thermodynamic properties. We have temperature, mass, volume, density, enthalpy, entropy, and so many others, right? So we will discuss that next time. But the point here is that whenever there's a crossing of energies at the boundaries, then there is actually a change in the system. Okay, another terms that we'll introduce is the state, processes, and cycle. So when I say state, it refers to the condition of a system as described by its properties. So, for example, here our piston and cylinder device again, and let's say here's our system, the gas. So at this point of the piston, let's say that's going to be point 1 or state 1 or point 1, and at that point there is property. There are properties that's going to describe the condition of this system. So it has a volume as well, and it has this pressure and also many other properties. So if we graph here, let's say the pressure and volume graph, so you see here that we have a higher volume. So at this position of piston, we have a large volume, but the pressure is low. Then because of energy crossing the boundaries, let's say we input work into this system, then that means there is a change in the volume. So from state 1 it moved to state 2. At this point, state 2, and then there's gonna be change in the pressure as well. So actually it depends upon the process, but for this given example, there is this change in the volume and the change in the pressure. Okay, so that means at state 2 we have a low volume, but we have a higher pressure. So this is another state. So again, when I say state, it refers to the condition of a system as described by its properties. So because of the energy transfer, the condition actually changed from state 1 to state 2, and the change of the state, this change of state is what we call process. And then we use the term cycle if it is a sequence of processes that goes back to its original state. So that means, let's say we have this graph again. So initially it started here, and then it moved to some point, to some state, then it goes back again to its original. So this is a cycle. Okay, and then next is the concept of thermodynamic equilibrium. The word equilibrium actually says, or it means that there's no changes in the system, but changes in what sense or in what aspect. So we can have, or we can say thermodynamic, or an object or a substance is in thermodynamic equilibrium if in terms of, let's say, temperature. So thermal equilibrium is thermal equilibrium. So if the temperature in that system is uniform all throughout, or there's no changes in the temperature, then we say that it is in thermal equilibrium. Then in terms of mechanical equilibrium, when we say that the pressure is not changing anymore, and then we also have this other equilibrium like the phase of the substance. Let's say it's purely a liquid, it's not changing, it's not changing to vapors, so there's not a mixture actually. Okay, and then or if it's mixture, then as long as there's no changes when we're considering mixture, then that means throughout our analysis it's going to be mixture. So there's also equilibrium for phase, and also we have, I think, chemical equilibrium. So when the chemical composition does not change with time, so actually changes with time, with respect to time. However, this is actually an abstraction. So it says here it is really an abstraction, as real systems are never strictly in equilibrium. However, we postulate that any thermodynamic system can be in equilibrium after it has been left to itself long enough, so that at least the variation is the variation is, we can say, negligible. So like for example, initially we have this water, then all throughout the temperature, let's say it's all throughout after some time, so all throughout it's gonna be uniform, or we say it is in thermal equilibrium. Or if we start heating, of course, at this layer first, or at this layer of water, of course it has higher temperature than the layers above. But after some time, actually, it can achieve a more uniform temperature all throughout, and we can say that it's going to be in thermal equilibrium. Okay, so next is the other laws of thermodynamics. We mentioned earlier about the first law and the second law. And we say that this is actually the basis or the main principles um, of thermodynamics. One concerning the energy, and the other one concerning the entropy or the dissipation of energy. But still there are still any other many other laws or principles: the zeroth law, the third law, the state postulate, and even other laws like the mass conservation. So let's discuss it here. When I say zeroth law, basically the word zeroth, that means in terms of discovery, the first law and second law was stated first, but then they found out that, I mean, after some time, they found out that the idea about the zeroth law must be fundamental. So that means it has to be the first one. But since there's already first, then it cannot be the first one, and that means they uh, they name it the zeroth law. Right, so because it's just fundamental. But the idea is this, with regard to the temperature. It just says that if the temperature of A, let's say the temperature of, let's say we have three bodies here, A, B, and C. So if the temperature of A is, let's say, 25 degrees C, and then if A is equal to B, that means B is also 25 degrees C. If A is equal to B and B is equal to C, that means this is also 25 degrees C. That means A is equal to C. So it's a logic actually. But the application is actually with regards to thermometry. So let's say we have some temperature here, I mean a body with some known temperature, and we have another body here, let's say the body B, then we have a third body, and let's say this is the body C, or the thermometer. So we can say that they have the same temperature if I measure this C, if I measure this thermometer here to A and measure it to B, and they have the same reading, then that means they are of the same temperature. But if it's not, then there's going to be changes in the temperature. So for example, if this is my basis, let's say the ambient condition is my basis, and I set this or calibrate the instrument, set this to 0 with respect to this, then if I measure the B, then if I get the same reading, then that means they are of the same temperature. But if not, then it means that they are not, they don't have the same temperature. So that's why you say that the application of this is in terms of thermometry. Okay, next one is the third law. Third law, this is just the basic statement so that we can relate it to the other two, but actually it relates to the, if I'm not mistaken, is the Nernst law, and it relates to the crystalline substance. But the idea is that we can have an entropy that is 0 as long as we get to this absolute temperature. And when I say absolute temperature, we have negative 270 degrees C. And we can have 0 entropy. So recall that in the second law it says that entropy is generated and it's never destroyed. Entropy is generated and is never destroyed. So that means if we have more, or if we are at higher temperature, then that means we have more entropy. But if we get down to negative 270 degrees C, that means we can achieve a 0 entropy. So at this condition. Okay, and then next one is we have the state postulate, and basically this is about the, if we know two properties of a pure substance, then we can actually find the other properties. Okay, so I think that's all for this other laws of thermodynamics. We also have the mass law, or the conservation of mass. So mass is conserved. Anyway, we will discuss that next time. And then lastly, we have the units and measurements. So measurements are used to quantify physical quantities, like for example, length, time, mass, and it is based on some standards. So it must be understood that the measurements that we're using um, is based on some standards. And we have these two systems for measurements. We have the SI and the IP systems, or the English systems. English systems, IP or inch pound systems. Inch pound systems and the system, international system of units. So for the quantities like mass, length, time, temperature, force, energy, power, and there's actually a lot more. Then we have here the units based on SI, and we have units based on the English systems. So for SI, the base unit for mass is in kilograms, and the length is in meters, and the time is in seconds. For inch pound systems, we have the slugs, or we use pound mass more often. So pound mass, it's different from pound force. And for the length, we have feet, we also have inches, and still many other lengths, but the base one are these ones that's written here. Then for the temperature, we have Celsius, and we also have Kelvin for absolute temperature, and here Fahrenheit, and the absolute one is the Rankine. For the force, we have Newton, and here we have pound force. And for energy, work, or heat, we have here the units joules. And for inch pound systems, we have the BTUs, and also we have the foot pounds. Right, so foot pounds, that's a unit of energy as well. So this is different. This is not the same as the pound foot. So this foot pound is the energy unit of energy, while the pound foot is a unit of moment. It's a moment. And then for the power, that is the rate at which energy is used or done. So we have the unit of watts. So watts is just equal to joules per second. And here we have horsepower, and we also have other units like foot pound per seconds, or foot pound per minutes. So there's going to be conversion for that. Then sometimes we need to convert one unit to the other. So therefore, we need to know the conversion of the units. So let's say from 1 meter to feet, we have 3.28, and 1 foot is equal to 12 inches. 1 minute, 1 kilogram is 2.2. Take note, pound mass, and then 1 BTU is 1055 joules, and 1 joule is equal to, and so many. Actually, if you just know some, then you can actually work on it. So in terms of conversion, let's say I want to convert 3 meters to feet. So what I will do is, here's our conversion. We can write it as 1 meter is equal to 3.28 feet. So this is a conversion. Or we can write it's the same thing as 3.28 feet is equal to 1 meter. Right? So that means whichever unit that I will need, I can write it in whichever forms. So let's say convert 3 or 6 meters, 6 meters to feet. Okay, so I will write, let's say 6 meters times okay, so I will use this because I want to cancel out the meter, so that means 3.28 feet per 1 meter. So therefore, more or less is around 20 feet. See, so we see here that the unit of meter is cancels out, and what's left is the 3.28 feet. Okay, so that's why we have 20 feet. Okay, next one is, let's say we want to convert, let's say convert 3 feet, 3 meters to inches. So that means, if I only know this, that means 3 meters times 3.28 feet all over 1 meter times the conversion of feet to inches. 1 foot is equal to 12 inches is equal to some value, and the unit here is in inch. Okay, and then last is, let's say we want to convert 100 joules. Let's say 100 joules, say 100 joules per second, or maybe we'll use this 746, or let's just say 100 watts. So 100 watts convert to foot-pound per seconds. Okay, so first is, let's write the given 100 watts times the conversion. So what we know is watts to HP. So 746 watts is equal to 1 HP times the conversion of HP to foot-pound per second. So since HP is in the numerator, that means here we have 1 HP is equal to 550 foot-pound per seconds. And we get an answer here of foot-pound per seconds. Right, so watts cancels out watts, and HP. So foot-pound per second is the last unit. Okay, so I think that's all for our topic number 1, and in the next video we will discuss the next topic, the topic number 2, which is the thermodynamic properties. So see you in the next video.